Hello everyone. Today we will see about what is Sieve of Eratosthenes, which is an efficient algorithm to find all prime numbers from 2 to the given number n. And we'll see how to make it more efficient with the help of parallel processing using OpenMP. So, how does this work? First, we create an array of n integers. In this case, let n be 100. So, we create an array from 1 all the way to 100. But we neglect one because it's neither prime nor non-prime. So starting from 2, we know 2 is a prime, so we can mark 2 as a prime and mark its multiples as non-prime. So we neglect 4, 6, 8, 10, 12, yes. And then we move to 3. And 3 is also a prime. So we mark 3 as a prime and we remove its multiples, that is 6, 6. And then to the next. We come to 4. But since 4 is marked as a non-prime, we will skip the number and go to the next number, that is 5. 5 is a prime, so we can mark its multiples as non-prime. Then we move to 6. Again, it's a non-prime, so we can skip it and go to 7. And mark its multiples as non-prime. Then we can skip 8, 9 and 10 as they are all non-primes and move to 11, which is prime. And mark its multiple just non-prime. It is 22, 33, 44, all the way to 99. Okay, all are marked. Okay. And we can skip 12 and go to 13. Again, 13 is a prime. Yeah, that's it. Then skipping 14, 15, 16 as they are non-primes, we can go to 17 and mark its multiples. That's 17, 34, 51, 50, 60, 85. Oh, no, that's it. Then 19 and similarly 19 is also prime. So 19, 38, 57, 57. Also, and if we keep on going like this, we'll get every non-primes marked as a non-prime, and we will be left out only primes. So we check here, we primes are 2, 3, 5, 7, 11, 13, 17, 19, all the way. So 23, 29, 31, 37, 41, 43, 47, 53, 61, 71, 73, 67, 59, 79, 89, and 97, which leaves us about 24 primes. So from 2 to 100, we get about 24 primes. Okay. So now if we see a main function for the code, we can see that we are using file handling to read the limit from a text file. In this case, our limit will be about 10 million, and we pass that as a parameter for the function. So if you have a look at a function, we can see int limit as a parameter and int memory size. What is this? This is done considering only odd numbers can be a prime, as even numbers are always a multiple of 2 and they cannot be a non-prime. And then we allocate a boolean array for that many integers, and at the beginning we mark everything as true, assuming it as a prime. So what does this for loop do? This for loop basically marks all non-prime numbers. And why is it I is equal to 3? Since we know 2 is a prime, so we can start from 3, and this runs all the way till square root of the limit. In this case, as the limit is 100, the square root of limit is 10. It runs from 3 to 10, going every two numbers, as only odd numbers are present. If the given number is a prime, we proceed to mark all its multiples as non-primes using the second for loop. And what does this found mean? This found is just counting how many primes are present. If the limit is greater than 2, we assume it found to be 1 initially, and we run another for loop and check every element in the array. Whichever element is true and that is unmarked, those numbers are prime, and we increment the found with respect to it, and then we later return the found. How do we approach this in a parallel manner? Parallels also the similar. First, on what the first line here is setting number of threads available with respect to the number of processes we have right now. And the limit square root is just another variable for this for storing the square root of the limit in. And memory size. Memory size is considering only odd numbers, and we create an array for that many integers. So what does this directive mean? Pragma OMP parallel for. This schedules the number of threads available and distributes equal chunks of data for this for the for loop. The for loop, suppose from 0 to memory size, in this case it's 0 to 10. It distributes equal data to it. It distributes 2 to one thread and 4 to another thread. It distributes data to it and performs operation. Similarly, what does this pragma OMP, this directive here? A dynamic scheduling is basically it decides a runtime how many how much big of a chunk of data should I give for a thread. This is helpful as it can run two for loops, so we can distribute this for loop to one thread and perform the operations, and similarly we can do the rest. And similarly same thing is found here. This reduction plus equal 4. This basically means that in a thread, suppose it runs from 1 to 10. In this case 2 to 10, we get 4 primes. Similarly from 11 to 20, we get around 4 primes. What it does is, it stores a found variable locally in the thread and adds up how many primes are present. So in this case, if thread 1 runs from 2 to 10, we get 4 primes. Similarly, in another thread, we run from 11 to 20, we get 4 primes. Those values are stored locally. So what reduction does here is, it adds up the locally stored variables to the given variable here. In this case, it's found. So if thread 1 has 4 primes and thread 2 has 4 primes, it adds them both to the given found here. And later it's returned. So if we see the runtime, considering the limit to be 10 million, we can see that if we run we can see that sequential manner takes about 112 milliseconds, while parallel takes only 0.068 seconds, that is 68 milliseconds. If we see its efficiency, we get that we get it to be 1.65 times more efficient. This increases for a large data set. Suppose we go for 1 billion, we can see it. We can see the sequential took about 17 seconds while parallel took 11 seconds. That brings us 1.5 times more efficient. On an average, we find this code to be around 1.5 to 1.6 times more efficient than a sequential manner.